Sancar from Trakya University.
First of all, I would like to thank the organizers for giving me the opportunity to speak here today. So today I'm going to talk about the DPD parameterization that we perform in order to model it with variable volumes, variable beat volumes, and to extend the parameterization to hydrogen bond interactions. Okay, so there was nothing specifically mentioning the simulation on the title, but here from this cartoon you can immediately understand that today I will also talk about a bit of simulations. So initially I will start with a brief introduction of the concept, and later I would like to give a brief for the general application of DPD. And later, I would like to go more into detail of how we describe the variable beat volumes by DPD and what is the necessity behind it. And later, you can also see this as a second stage, the hydrogen bonding in DPD. And I will finish my talk by briefly summarizing and the current status and what could be applied as future studies. Okay, so I would like to draw your attention to the concept that imagine that you would like to simulate or you would like to estimate the properties of a complex chemical structure. It can be oligomer, it can be polymer, and it can be also reacting with an isocyanate. So this specifically structure, this is a particular structure, but you can also try to apply this for a variety of systems. And imagine that you would like to study these type of systems which are already reacting, pack units and the isocyanates, and giving you a physical crosslinks which are actually happening after chemical formation, and your structure even is becoming more complicated. So which is actually you can refer as the polyurethane network. And so you have the structure at hand, and what you would like to have at the end, or your interest, is can be either molecular structure at the equilibrium, so you can either study it by just plotting the snapshots. This is just an initial starting point, and also you can perform even more quantification by further computing radial distribution functions. So this is just two examples. You can obviously extend the range of your molecular structure evolution. At the equilibrium state. So this might be one interest. The second interest can be also the properties at the equilibrium. For example, the Poisson's ratio, the elastic modulus of the material, or glass transition temperature, Tg, etc., etc. So you can either estimate this from equilibrium structure, as I mentioned, or eventually towards the equilibrium structure you can compute the instantaneous fluctuation of the simulation box, and from such a relation it will already give you an estimate of the Poisson ratio, elastic modulus, and the bulk modulus. And for the glass transition temperature, you can ultimately consider the simulations at different temperatures, and from the interception point you can read actually the glass transition temperature. So these might be the points that you are interested to study in a polymeric system. So if this is such a point, the title was already, and the cartoon secondly was indicating the simulation point of view. You can approach to the problem by, computationally, and a variety of techniques. One of them could be quantum mechanical simulations, but this is limiting because you can only simulate a few order of magnitudes in order to model the chemical reactions or the electron density around particular atoms. You can either perform continuum mechanics simulations in order to estimate, for example, the fracture behavior of the polymer or different variety of systems. But our particular attention in this presentation is actually falling at this stage, falling at this phase of the length and time diagram. And for such a system that I've already shown you in the first slide, you can all imagine to go through with the atomistic simulations first. So what would it bring you? So you would have at the end, after performing atomistic molecular dynamic simulations, the explicit atomistic structure, and you can, in principle, quantify the energetic, physical, and material properties. But as already mentioned, the having the system of fully cross-linked, the initial formation of the cross-linked and later the equilibration might be a problem due to the relevant time and length scales associated with the molecular dynamic simulations. So what you could do is to consider the simulations, the molecular simulations at the higher length scale, which are called referred mesoscopic time scale, or you can even call these coarse grain simulations, in order to reach higher times and length scales, and they evaluate the structure afterwards. So coarse graining is actually, for those of you who are not completely familiar with the idea, coarse graining is if you have an atomistic structure, fully atomistic structure. Coarse graining means collecting some functional groups together and forming larger entities which are called as beads. So in these formation of these beads, the whole atomistic detail is completely integrated out. So what you have is the point particles in the Cartesian space. So this is more or less what you would like to have for a structure generation, for in particular a coarse-link system, by using some statistical methods like combining or formation of a physical bonds if two beads are in a close proximity, something like this. You can have your cross-link structure at the end. And for the, if you want to really go to the, if your interest is performing simulations for the material properties, you can even perform fine graining, reverse mapping, or back mapping, which you can use whatever terminology you would like to have, and later, as I mentioned, perform atomistic molecular dynamic simulations. So this is more or less the bridge that one can think of a logical and feasible way to perform it. Okay, so I'll just remind you the initial structure that I showed you at the beginning, the cross-link structure, the polyurethane pack polyurethane network. So if you would like to apply this coarse graining to this type of system, upon chemically meaningful partitioning of the molecule, you would have coarse grain structure or beads, as can be seen. And here you can see that we have different beads, and the prime ones are indicating actually the beads that are formed after chemical reaction. Okay, so I just briefly wanted to show you what beading is, or what coarse graining is, and I try to give you an overview of a molecular simulation can be applied to study such type of system. And here I would like to talk a little bit about the title, which is actually referred as dissipative particle dynamics, and the title was already mentioning about the alternative parameterization of this method. So initially, why do we need this parameterization? I will explain it after what is the conventional DPD is used for. So the conventional DPD method, dissipative particle dynamics method, is adopting the similar idea of molecular simulations. So the time evolution of the atoms, particles, whatever is actually solved by computed or set force. And then the integration of this gives already the time evolution of the particles. And this force in DPD is composed of three parts: conservative, random, and dissipative forces. And the conservative or random, conservative force already characterizes the equilibrium structure, and random and dissipative forces are actually coupled, and they are acting as a thermostat. So this is a nice feature of DPD. You don't have to bother yourself with trying to find a suitable thermostat or biostat for your simulations. So the heat dissipation and so it's heat source and sink behavior that is already associated with these type of coupled forces already gives you a nice control of the temperature. And the potential that we use for DPD is actually, for the non-bonded, obviously, potential is a soft one. So you can see also from here, and fully repulsive one. And some years ago, Groot and Warren in '97, they came up with the idea to parameterize these pairwise interactions by adopting the parameters from the experiments, which is actually in this case Fuller-Huggins chi parameter, and they actually nicely established a linear relationship between the DPD parameters A's and the experimental parameter chi. So what is valid in this conventional DPD is the assumption of equal size beads. So which means if you have a system, completely phase separated, so you can think of these beads, a soup of beads with A and B. If they are phase separated or in mechanical equilibrium, they would already give two phases with same density. So this is represented in DPD by adopting same like interaction values. Like means the interactions in between same type of particles. So if you really would like to apply DPD to more complicated system in which you cannot divide some functional groups to two or so, which would already give you same order of magnitude or same values for the volume, this might be a problem. So the initial part of my talk would be about the parameterization of this. So what I want to say is actually, if you have, for example, the parts phenyl groups plus the D beads here, which already order of factor 3 different. So this is what we would like to have at the end, is actually if these beads are simulated in the same way that I showed in the previous slide, if they're simulated in a mechanical equilibrium and phase separated, but you would have two different phases with the number densities are actually their pure correlated with their pure liquid densities. So that means you would not have a like interaction which would be similar at the end. So what you do is actually play with the compressibilities to generate different volumes around beads. Remember, I already mentioned that these are point particles, so that is what is important is the volume around the particular bead. So the parameterization is actually coming from the DPD equation of state. So initially what I would like to show you the like interaction parameter. So this is the DPD equation of state with a constant alpha above a number density of 3. So you can just take to one side and establish a relationship for the like interaction. So you can compute this for any type of bead in the system. But what is interesting here, what the combination of these values, because you can already imagine that what happens if A and B type of beads are mixed together. So you have to define also a pairwise interaction in between them. So the initial part of the pair interaction is the neutral interaction, and is already coming from the assumption that the pressure is hugely dominated by this part of the equation, and by using the conventional mixing, what you would have at the end is such a relationship. And if you apply the DPD equation of state for a mixture, and then in the mixture you wouldn't want to have an excess pressure, and the only constraint for this is to use a neutral interaction parameter, and our derivation is actually following in this respect. So what you have already, we have this relationship, and we have already this one. So if you expand this by taking just the square and the usual, the opening of the squares, and what we have at the end is actually when you insert this one, we have already the relationship as you can see in the slide. So as I mentioned, this excess pressure shouldn't be there. So this part is actually to be 0 in order to equate right and left hand side. And what you have at the end is just a Berthelot type of mixing. So this was only for the neutral interaction, that you wouldn't have the excess pressure. And what is also important in DPD to apply it to really parameterize actually from the experimental values is mapping on the Fuller-Huggins parameter, as Groot and Warren did, as I already mentioned before. So we actually started to this by considering, okay, maybe you are not seeing, but what you see here is actually different pressures that are applied to the system. And here you see the chi versus the delta A, which is the difference in between the effective repulsion strength with respect to the chi, and the chi is actually computed from the Fuller-Huggins mean field theory. So here, for different pressures, you can see that all the points are overlapping on each other. And that means what you would have at the end in terms of phase mixing wouldn't be affected from the pressure value that you select. So this gives quite a number of flexibility to you by applying this procedure. And if you would like to consider different bead sizes, in this case, the situation gets different and they start to deviate from each other. So what you would do, try to find a relationship, because this is the Groth and Warren line, and our aim is to find a relationship in between them. So to come up with a scaling factor that would reasonably explain this type of curve. So what you see is actually a scaling. I mean, in the next part, which will come here in the equation, you will see this is much more clearly, I presume. A line in the form of like this relation reasonably explains nicely actually, and for the practical point of view, we would also like to consider a linear relationship and go for that. So this is actually more or less what we would have at the end. So this is the mapping of the DPD parameters for the variable bead sizes to Fuller-Higgins chi parameter. For a validation, you could compute the chi parameter for, again, artificially phase-separated states and try to compute a critical value. So this is, in this case, in a fair comparison with the Groth and Warren prediction. So you can also argue that, okay, this might be high, but you also have to think about the practicality of the concept. And applying to real systems, the situation gets, I mean, the comparison, the validation gets even better. So what we did for the different bead sizes, so we actually performed a Voronoi tessellation to the mixture of beads which are composed of this system. So there are no covalent bonds in between beads. And at the end, we predicted nicely the sequence of the bead sizes, plus these beads are, I mean, in DPD units, are actually fitting to the liquid equilibrium, pure liquid volumes of each individual bead. So you can find more information in these publications. And by using this type of an approach, where we consider the alternative volumes, you can even consider a parameterization of the mesoscopic DPD particles with respect to a solid interface, because this was already give you the compressibilities, or already makes beads hard and soft, so you can either play with the compressibles to make a hard surface. So as I mentioned, this was a polymer surface interaction or bead surface interaction. So what you could do is to couple atomistic and DPD scale by means of surface excess values. So initially what you would need is atomistic simulations for each type of bead, and then you compute the surface excess, and at the same time you can construct a master curve where you can actually, after having the sigma from the surface excess, you can read whatever DPD parameter you would like to have. So this actually plot is constructed for each type of beads, and there's a scaling factor here where you can have at the end the master curve. Okay, so this was more or less what I said, and yeah, this is the result that at the end we had. Okay, so initial part was about the variable bead volumes, and the second phase is like the hydrogen bonding that we applied for the DPD parameterization. So here, the driving motivation is coming from the self-replenishing hydrogel. So I just, in a minute, what I want to say is the self-replenishing concept. So imagine that you have a polymeric functional surface, and upon damage, these functional groups can wear off. And what you would have at the end, would like to have, is recover the surface functionality. So the idea for self-replenishing polymers or hydrogels, it cannot be hydrogel, that's not necessary. But in order to recover the surface functionality is important in order for the operation properties. And in this case, in our case actually, this is embedded in water, so water interactions are important. That's why we consider the hydrogen bonding. Okay, so that was more or less what I said. And yeah, you can already extend it if you would like to model polymers in physiological conditions. So the hydrogen bonding in TBT is coming from addition of an additional term to the total DPD force. So this is the force is added in terms of a Morse potential. So you need to parameterize the Morse parameters. And in this case, we consider two parameters in the Morse. That was what is there in Morse potential: the hydrogen bonding distance R0, and then the depth of the energy well D0. So for this, we wanted to consider a test system, which are methanol water, ethanol water, and one propanol water. So we actually more or less started parameterization of the system right away for these mixtures, which are experimentally known to have negative volume excess upon mixing. So the R0, the equilibrium hydrogen bonding distance, is computed from the radial distribution functions, from the minimum of the functions, where we would have already the non-bonded distance, and the D0 is computed by mapping the mixing energies. And at the end, you would have values. D0s is a function of the concentration, and the R0 is actually more or less similar. So here you would have some sort of a difference, but you can imagine that we are not considering the directionality also at the surface. So this might be, I mean, this could be, but probably this is the reason why we are having the different values for the R0. But the structure is actually predicted in the next slide, as I showed in the next slide. So as I already mentioned, this gives a negative volume excess for these alcohol-water mixtures. And here I would like to show you that if you would like to do this with a conventional DPD procedure, you would always have a positive volume excess. And this is the behavior for the experiments. So here, for the methanol water case, ethanol water case, and the propanol water case, and the lines are experiments, and the dots are our prediction, you could even see that very nicely fit is observed. And not only the points are predicted, but also the location of the curve the shape of the curve is predicted, and this is the shape of the curve is actually dictated as a function of the different bead sizes. Here, I forgot to mention that we take each alcohol molecule and water molecule as one bead. Okay, so the next check on this type of mixing behavior is actually there's the experimental evidence on the surface enrichment of alcohols at the interface. So here you have the air. Modeling air is actually only performed by introducing a repulsive strength in between. And what you have at the end is actually an agreement with the experimental behavior. As I already mentioned, so you can already detect these gaps, but what we have is just a set an arbitrary repulsive strength in between, and I mean, this might be veer off if you consider a more logical approach to mimic air. But that is also another, so this was not our object, and we didn't really go in that respect. Okay, so I just briefly want to show you a couple of results on the application of this type of parameterization for the hydrogels. So we have different water contents in the total mixture, so greens are water. Here in this case, just switched off the hydrogen bond interaction, and you see that in a hydrophilic polymer, you wouldn't expect a phase separation of water. And for the, when we switch on the hydrogen bonding attraction, and for 25%, 50%, and 75%, you would already see that in 3 snapshots and in the density profiles, the water is distributed inside the polymer. So we are still, performing some simulations in order to estimate the swelling behavior to couple with the experimental data. Okay, so the last thing that I would like to tell you is the hydrogen bond interactions between water beads. What I was already telling you before about the parameterization was only valid between the alcohol molecules and the water molecules. So there was no hydrogen bonding interaction in between water, but that is obviously important if you really would like to study the surface segregation of some functional groups or hydrophilic groups, whatever, because water also have to preferentially attract to each other, and the coordination of water around packed beads is actually heavily influenced by this difference of the preferential attraction. So what you would theoretically imagine that hydrogen bonding of water is more or less like this, but as I already mentioned, we don't have the directionality. Also because of the reason that the time step in DPD is already much larger than the hydrogen bond dissociation times. So again, a similar approach for the Morse type of potential added to the DPD conservative potential. And yeah, from experiments, you might imagine that you already know this because hydrogen bonding in water is actually studied yeah, for a very long time. So you have already the energy strength in between two hydrogen bonds, and you already have an experimental prediction for the R0, which is the hydrogen bonding equilibrium distance. But what you don't have in the, which is not known actually, so these are known, which is not known is actually the sigma, which is already the curvature of the Morse potential. So the current status where we are now is already thinking about how to estimate this. We have, so which is actually physically means, what it physically means is actually the force, constant of the stretching, and we are thinking about estimating it by applying, by computing the spectral vibrational frequency of water center of mass, for which water center of mass, and try to estimate this, but still we are working on that. Okay, as a summary, today I wanted to give you a brief overview of an initially the conventional DPD, and later DPD parameterization, how we approach to compute the variable beat volumes. And later I wanted to show you the hydrogen bonding implementation in the DPD method by considering this multi-scale parameterization, and already showed that physical properties of some liquid binary mixtures are predicted nicely. And what the outcome with respect to the structure and some physical properties of the hydrophilic coating. And currently, as I mentioned, we are working now on the water-water hydrogen bonding interactions, which would eventually alter the properties of the local properties of, in terms of coordination of water beads around polymer beads. So first of all, I would like to thank you for your attention, and the rest for funding and my collaborators.
I have a question related to this propanol water. It's something very weird. I mean, what's happening there?
The mixing?
Yes.
So upon mixing of these low molecular weight alcohols with water, yeah, experimentally it's known that there is this negative, there is a volume shrinkage. So the volume is lower than V1 plus V2. So that is more or less what happens. So, but the other alcohols, they also there. I mean, yeah, I cannot comment on the different type of alcohols, but for this type of system, that is more or less there. And also for polyethylene glycol with the molecular weight of 400, similar cases there. Because of hydrogen bonding and also the coordination of water around pack beads, or the hydrogen bonding with respect to the alcohol beads or molecules, which you could already imagine that this is dominating the end physical structure. Okay.
Any other questions? Okay. So a short question. How about the torsional effects?
Sorry?
Torsional.
The torsional effects, yeah, because I mean the torsional effect. You mean the in the, yeah, that is already taken into. First of all, I didn't mention here, but in order to apply the DPD to polymeric systems, we already consider the bonded interactions, the angle potential, and also the torsional potential. We parameterize it based on the proper molecular dynamic simulations, and then try to map it to the harmonic potential. Yeah.
Let's thank the speaker.